Today I'm going to run through this quick workshop about normal populations and Bayesian statistics. So we've seen how Bayesian statistics can be used with proportions and with other statistical models involving things like the uniform distribution or the Poisson distribution. And today I want to take a look at what is probably the most common situation in statistics, where you have a population that you think might have a normal distribution and you want to say something about the population mean. And to simplify things, I'm going to assume that you know the population standard deviation. So I'm going to assume that this number sigma for the population is known. That actually is a pretty big assumption. In statistics, there are relatively simple workarounds, but since we're just scratching the surface of Bayesian statistics this semester, I think it's okay to pretend that we know this number and just sort of move on. So here's a theorem that says how this all works. If you start with a normal distribution for your prior, and you have a normal distribution for the population of interest, then the posterior distribution is also normal, and that's this theorem. In fact, not only is it normal, but it's actually relatively easy to calculate the updated posterior mean and posterior standard deviation. So this theorem has those two formulas in it. So the posterior mean is right here. It's this formula. And the way this works basically is you start off with your prior mean, where you think the average might be. And then you go collect a sample, and you get a sample mean. And what you end up doing is you sort of take a weighted average of these two numbers, where the weights are these two fractions, alpha over alpha plus 1 and beta over beta plus 1, where alpha and beta are these two fractions here. So you're always going to end up with a posterior mean for your parameter that's somewhere in between where you started with assuming in your prior and where you got in your data. So you're sort of updating where you think the average might be based on your data, and it's going to be somewhere in between where your data was and what your prior was. And then there's a formula here for the standard deviation, and again, similarly, it's somewhere between the original standard deviation tau in your prior and this new standard deviation, which is, if you look at this, you can notice that this is like the reciprocal of the sample variance of x bar. So okay, moving on. I'm not going to prove this theorem. It is in our book. If you read example 7.1.2, they walk through the actual proof of this. It's not too bad. I thought about making that a workshop, but I figured it would be just a little more than I want you to have to do right now. So instead, I just gave you the theorem, and let's just use it. So last year, as I did in another example, we had this data set of my 47 students. And one of the things I asked my students was how tall they were. And based on that sample of 47 students, I was able to get a sample mean for the heights of my class. And I had the average height of the students in my classes was 71.85. And that sample is going to let me say something about the population of all Hampton-Sydney students. I want to know what is the average height of all Hampton-Sydney students. Now, I couldn't get a sample of everybody, so instead I have just a small sample. And based on this small sample, I'm going to update a prior distribution and say that I'm pretty confident that this distribution contains the population mean. So how do you do that? Well, I need a prior distribution to start with. And so here I sort of outline the thought process for how to choose a prior. When you're working with a normal population, usually the right prior to choose is a normal prior. And so I've got to think about what I think the average height of Hampton-Sydney students might be. And so I start off with what I know about the United States. In the United States, men in the United States have an average height of about 70. And so I might guess that that's probably true for Hampton-Sydney students too, that they're about the same as everybody else in the population, or at least all the other men in the population. And so I might say, well, maybe the average height for Hampton-Sydney men is 70 inches also. Then I also need to pick a standard deviation for this prior distribution. This doesn't have to be the same as the population standard deviation, right? The population standard deviation, I'm assuming, is about 3, but my prior is modeling a different thing. It's not modeling the population, it's modeling where I think the mean might be. And right now I think that the population mean for Hampton-Sydney might be 70, but I think I might be off target a little bit. Maybe Hampton-Sydney students are a little taller or a little shorter than other men in the United States. So maybe I could model my uncertainty by picking a standard deviation of about 1 inch. Then I wouldn't be that surprised if the true number was about 1 or 2 inches higher or 1 or 2 inches lower. And I think that sounds about right. So I'm going to use that as my prior. So my prior distribution is the normal distribution with a mean of 70 and a standard deviation of 1. Okay, so then you do, the same kind of math you always do. You take your likelihood function, you multiply it by the prior. And I'm not going to work out the details. I'm just going to refer back to this theorem to work out the details and say, well, the result of that's going to be another normal distribution. And this is what the average of that new normal distribution is going to be. And this is what the standard deviation is going to be. And then I just use a calculator. I punched in my numbers. My tau 0 is 1. My sigma 0 is 3. My sample size is 47. Punch in those numbers and then calculate these two formulas here. I'll get the alphas and betas and then the mu 0. Well, I started with a guess that the mu was 70, so that's my mu 0. And then I have a sample mean that's much bigger. It's 71.85 from the data. Where is that? That's down here, 71.85. So I punched all those numbers in, and what I got is I got this posterior mean was 71.55 with a standard deviation of 0.401. So that's my posterior distribution. It's a normal distribution bell curve, and my best guess for the population mean is 71.55. That's the maximum likelihood estimator. And then this is the, well, actually, no, I'm sorry. That's not the maximum. That's the posterior maximum. It's not the likelihood maximum. So that's the posterior maximum. And then this is the standard deviation of the posterior distribution. Okay, next question I asked is, okay, if we use this posterior distribution, we can answer questions like, what's the probability that the average for Hampton-Sydney students is higher than the average for all men in the United States? Given that my sample was so tall, my 47 students had an average height of 71.85, that's suggesting pretty strongly that Hampton-Sydney students are taller than the average for men in the United States. And so if you just calculate using the posterior distribution now, the probability that the actual average for Hampton-Sydney is all the way down at 70 or less, that's just the left tail of the distribution. You can use a quick R command to calculate that. I did 1 minus the p-norm. Location was 70, middle was 71.55, and standard deviation was 0.401, these same numbers. And I got this. I got a 99.99% chance that the Hampton-Sydney average is higher than the average for the United States. That's really clear and nice and simple. I really like this. This makes it way easier to say things with confidence than you would with a hypothesis test, right? If I had done a hypothesis test here, my results probably would have been significant, but all I could say then is I have statistically significant evidence, and I can't say how sure that I am that I'm right? I couldn't give like a percentage of, what's the probability flat out that Hampton-Sydney students really are taller than average. But based on my prior, which I thought was pretty reasonable, I can do that. I can say I'm 99.9% sure, 99.99% sure, which is pretty cool. Okay, next question was to make a credible interval. To make a credible interval, you take your posterior mean, the middle of your posterior distribution, and then you just basically add a certain number of standard deviations, posterior standard deviations to that. If you want 95% credibility, then you just add 1.96. It's the exact same 1.96 you would have added to make a 95% confidence interval. And in general, that's how these numbers work. If you wanted a 99% credible interval, you'd use the same z star as a 99% confidence interval, right? Because it's the same reasoning. You're working with a bell curve. You want 99% of the data in the middle. Makes sense. Okay. When I did that, I got a credible interval that went from 70.8 to 72.3 inches. And what's supposed to be in here? Yeah, what's supposed to be in here is the population mean for our population of interest, which is Hampton-Sydney students. So I'm 95% sure that the average height of Hampton-Sydney students is somewhere between 70.8 and 72.3. This works a lot like a confidence interval. And in fact, in the second to next problem, I'll work through how exactly it really is related to the old classical confidence interval formula. Now, one thing that you might be wondering about is this is all based on my prior distribution, and I made some assumptions in the prior. I had to guess what I thought the population mean might be to start with. What if I'd guessed something different? And what if I'd used a different standard deviation here? The good news is the bigger your sample is in Bayesian statistics, the less your prior distribution matters. You sort of wash away your prior assumptions with the real empirical data you're collecting, and you end up, if you have a big enough sample, with a posterior distribution, it doesn't really matter what your prior was. This distribution, you're going to see, actually is going to come out pretty close, even though in number 4, I actually started with a totally ridiculous prior. So if I assumed at the beginning that Hampton-Sydney students were around 7 feet tall on average, which is, like I said, ridiculous, but let's say I had done that and then made a prior based on that, so my prior would have been a bell curve centered at 84 inches with some standard deviation, and maybe to be fair here, maybe if I think that Hampton-Sydney students are 7 feet tall, maybe I'm pretty clueless, so I'd have to go with a pretty big uncertainty level, so a large standard deviation of tau equal to 12. If I pick those two numbers and then use my data to update the prior, what I get, and again you have to go back to those formulas from the theorem, but when you do that this time, you get a posterior mean of 71.87 with a standard deviation of 0.437. And if you look back on the last problem, that's not that different, right? We're getting a posterior mean of just slightly higher, and the reason it's higher is because I started with a higher starting point. But already it's pretty close, right? The 47 observations that I made have kind of fixed my bad prior and given me a posterior distribution that's actually pretty reasonable. And using this new posterior distribution, my 95% credible interval is pretty close to my last one, right? It starts at 71.0, only 0.2 inches higher than the last one started, and it ends up 72.7, which is only 0.4 inches off of what the original one was. So definitely this was the better posterior credible interval and better posterior distribution because it was based on a more reasonable prior. But even if you started with a bad prior, it kind of comes out okay in the end. Now you do have to be careful about that. If you start with a bad prior and you set your uncertainty level really low and say, I'm absolutely sure that Hampton-Sydney students are 7 feet tall, then it's going to take a lot of data to fix that bad prior. So just keep that in mind. You definitely want to keep your priors reasonable. Either make a good guess at the beginning, or if you don't know what a good guess is, pick a large standard deviation to reflect that you're very uncertain about your prior at the beginning, and then things will work out okay with your bigger sample size. Okay, number 5, I'm looking here at a general formula for the credible interval. Basically, you take the formula for the posterior mean that I had in the theorem, and then you add or subtract a certain number of standard deviations, right? Either 1.96 if you want a 95% credibility level, or something bigger if you want a higher credibility level, and you can just look it up on a normal distribution table. And then times the right standard deviation, which is this guy. And I asked the question of what's going to happen if you let that prior standard deviation get really, really big. Which means, what if you're really not sure that your prior is right? So you pick a really high standard deviation for that prior bell curve to basically say, I have no clue where the true population mean is. Well, as this gets bigger, in the limit, as tau goes to 0, the alpha, which is this formula, is going to, as tau gets really big, so as tau goes to infinity, the alpha here is going to get really small. So alpha is going to go to 0. Beta is going to stay whatever it is. So this fraction is going to go away, so it's going to go to 0. And this fraction, on the other hand, the alpha goes to 0, the beta stays what it is, so it's going to go to 1. And so it's going to head towards 1. And so if I was just showing my work here, this would be a good way to show my work in like a Calc 1 class. That goes to 0, this goes to 1, and then what happens? Well, that term goes away. Then you just have x bar plus or minus z star. And then this alpha, again, that's going away because it's going to 0. And then 1 over beta, what's the reciprocal of beta? Well, it's sigma squared over n. And hey, that's a formula that we know, right? That's the formula for a regular confidence interval, right? X plus or minus z star times the right standard deviation, which is the square root of sigma squared over n. Right, that's and this is the x with a bar on it, right? The sample mean. So that's how you make a classical z distribution confidence interval. And what's happening is when you do a Bayesian confidence interval, you're getting slightly more precise information based on your prior. So your prior is sort of helping make this interval be a little bit tighter than it would otherwise be. Your standard deviation here will be a little bit smaller if you have a little bit of alpha. But as you get less and less sure of your prior, as the alpha gets smaller and smaller, it kind of goes away, and then you just end up with a regular old confidence interval. So that's the relationship between credible intervals and confidence intervals. Credible intervals are a slightly more precise interval for your probability of finding your population parameter of interest, in this case the population mean. And the reason it's slightly tighter is because you can use the prior to sort of leverage it. But you have to be careful, of course, with the prior you choose. If you choose a bad prior, then you're going to be a little off target. Okay. As always, if you have any questions about one of these workshops, please let me know.